Hey, what's up, guys? Yeah, so today I want to prove that I want to show that the scheme theory, the scheme that the structure shift that we defined before is a radial shift. So basically, this will follow the Hartson's proof, but I will write more carefully, so step by step. And I mean, Hartson showed that very very skip a lot of details and right now not write things not so clearly. Okay, so yeah, let me just start. Hope you guys subscribe to my channel. Also, our goal is to show that the skin, right? So affine skin. So we define X to be the spec of A. So A is the prime ideals, which is prime ideal in A. So prime ideals, P is prime ideal of A. And then we define the distinguished open set D of F, which is a prime ideal that the F do not contains the prime ideal. F is the element of the ring, and then we define the structure sheaf. The structure sheaf defined on the distinguished open set. Since we show that distinguished open set will span the whole, will be the basis of the X. So we can define this to be the localization, the ring of localization. Okay, so I want to claim that this is a radial sheaf. So so basically it's a ring space. Okay, so it's a sheaf. Okay, so this is I think this is maybe the first time that you really start from sheaf axiom and prove something which is really a sheaf. Okay, and let me just write down. This is just x divided by f of n, where x belongs to band notation. Let's call it y. So y belongs to a. Okay, so usually people will write like this way. So we have a goes to a fi. And goes to a fi fj ij goes to this. Okay, so to really prove something is a sheaf, just make this sequence to be exact. Okay, so A is a ring, AFI is a ring localization for so we need to provide that we need to say that A is span by or ideal generated by F1, F2, let's say up to Fn. And this is the if and only if the same as the spec A. X is the union of the distinguished open set I from 1 to n. Okay, so provide we have this, and then we have this sequence just for A mapped to, so this is, let me just write down. So this, if we have S element here, that this map will just localize, right? So just S, 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 S. So for each is S restricted on F1, S restricted on F2, S restricted on F3, S restricted on Fn. And for this one that if somebody gives you S1, S2, Sn, then you can just localize on if there has intersection, right? So you can restrict it. Okay. Okay, so we want to show that this sequence is exact. We'll prove that it's the same as you prove the sheaf conditions. Okay, so the first one, this one is very simple. So this is the first one. Okay, so the first one, what we need to show is that as a sheaf, right? If we have, so we want to show that if there's somebody give you S belongs to A, and for each I S restricted on Fi 0, then we want to show that S equals 0 in A, right? So this is the same as the sheaf condition, right? If you have some guy which pull into 0, then you need to this guy must be 0. If there is a function on each restricted to each open set 0, that function on global one must be 0. Okay, so this is very simple. Let's prove. So since S restricted on Fi 0, so this is the same as S is 0 in localization AFI. So this means that there is this and let's say Mi such that Fi to the MIS is 0. Okay. The reason is that S restricted to Fi will just be S divided by 1. So S divided by 0 in the ring localization will just be provided there is Fi power that, and here it is S. Okay, so also notice that okay, so we have this. Okay, so also notice that our X, right, is a union of the whole space union of Fi. So since these are prime ideals, right? So we can just power them, right? So it's for each DFI is the same as DFI to the MI, right? So since we take the prime ideal which do not contain F, so if the prime ideals do not contain F, then it should not contain any power of F. Everyone in. Okay, so this means that the spec A, sorry, the whole space A is generated by the ideal is generated by F1 to M1, F2 to M2, up to Fn to Ma. Okay, so basically there's a Ri such that the 1, right, identity equals to Ri, Fi, Mi. Okay, so now we have this one, right? So we have this one, the rest will be very simple. We just times S both sides. Okay, so we just times S both sides. So we get S equals to I from 1 to N. Okay, Ri, Fi, MIS. Okay, so we have S equals to this. Okay, and but this Fi, MIS is 0, right? So it's 0. Okay, so very simple, right? So this is the just proof technique. It's really amazing, right? You start from ring localization, and for each localization that you have an equation, and you combine all these local equation, local data, and global one like this. Okay, and the next one, the second one will be a little bit difficult. What we need to show is that let's say we have F1 as F2 up to SFN, and suppose that there are Fi restricted on Fj is the same as Fj restricted on Fi as a ring localization for every ij. Then we need to find the S. We need to find S such that when S restricted on Fi will be the same as, or sorry, DFI will, sorry, D. Okay, restricted on DFI open set will be the same as SFI. So if we have a function which agree on all the, we have function which agree on every intercept, every intersection, then there must be a global function which generated. Okay, so this one is a little bit tricky. So let's write this function clearly. Let's write this as A1, right? So this is in local DFY. So let's write A1 divided by F1 L1, and A2 divided by F2 L2, and A3 divided by F3 L3, and yeah, keep going. Okay, and also AN divided by Fn Ln. Okay, and then let's say GI to be Fi Li. Okay, so since they are agree on each other, so we have AI Fi Li the same as AJ Fj Lj in A Fi Fj. Okay, so which means that you can find, let's say you can find the Mij power such that Mij G. Okay, so we have a Gij to the power. So we have, let's write down Gij to the Mij power such that AI Fj Lj minus Fi Li Aj is 0. Okay, so let me just copy it. So we have Gij Mij and Gj, sorry, AI Fj Lj, AI Fj Lj minus A J Fi Li is 0. Okay, so let's change the notation. So recall that we define Gi to be Fi Li. So this equation can be written as Gi Gj Mij Gj Ai minus Gi Aj 0. Okay, so now we take M to be the max of Mij. So in this case, I suppose it's finite. Okay, so we got the Gij to the power M, Gj Ai minus Gi Aj is 0. Okay, So now let's define bi to be ai gi for m, and hi to be gi m plus 1. Okay, so this is a, b, this is h. Okay, so combine these two, what we have is the hij. So this equation can be written as hij equals hjbi. Okay, so we have this. Okay, notice that the d of hi, the distinguished open SF of hi, is the same as d of gi, right? Because it's just power, and the d of fi, right? Because just power. Okay, so now we have the beautiful relation because we can write our x in terms of the union of dhi. Okay, so originally it's fi, right? So now we use the same thing, we shift it into hi, right? Okay, so now so that means that we can find, so there is ri such that rihi, let's say rihi, I from 1 to n, which is 1. Okay, so let's define r. Let me just define r to be the summation of ribi. Okay, so by the d of hi union of I from 1n, d of hy will be the spec of whole rings. Then there's a exists r such that rihi is 1. Okay, so I take all this hi and collect it into bi. I say I use the same notation. I say use the same number and plug it into bi to define a guy which r. Okay. Okay, so amazingly, this r is our answer. Okay, so let's check it. So if r times hj, will give me summation, I ri hjbi. Okay, and this guy is the same as ri. So use the previous formula that we got bi hj is the same as bjhi, right? So we can change into hibj. Okay, so which is the same as bj. Okay, so we get r equals to bj divided by hj. Okay, right? So I mean, we get rhj, right? So this means that when r restricted to j component, when r restricted to d of fj, this is the same as you restricted, you get bj divided by hj. Okay, so bj divided by hj is just what? It's just this, right? So if bi, you do di divided by hi, then you get ai divided by gi. Okay, so which is ai divided by fili. Okay, so amazingly is that if you define, so now you get your answer, right? You get your whole ring r. When this r, when you put this r, if you restricted this r, into this d of the distinguished open set of fj, which you will get, this is the same as bj divided by hj. So this equation is true in d of fj. Okay, because in this it's not in d of, it's the same as the structure sheaf ox, so it's the afj. Okay, so these guys, these guys the same as these are restricted to dfj is the same as bj divided by hj by definition, right? So you can check that since this hj times r minus bj is exactly 0, so which means that r restricted on dfj is the same as bj hj, and the bj hj is exactly the same as ai divided aj divided by fj to the lj. So now these are restricted on each distinguished open set is the same. Okay, so this R is what we need. So this R is just the global section that restricted on each open set will give you the results. Okay, so finally that so R is what we need. Oh, finish. Yeah, so R is what we need. So R is what we need. Okay, so this finally proved that this is just a ring space. If you check out this proof, this is the same as Harson's proof, almost the same. Okay, so now we finish the 3 steps of affine scaling. We prove, we give its set, and we give its basis, and we prove its the ring space. Okay, so now we have affine scaling as our starting point that we can start to learn more.